So today we're going to be looking at vectors and how we can use vectors when modelling in mechanics. So to start off, we'll revisit what you know from GCSE, and then we'll move on to some new conceptual knowledge and some skills that you need to be fluent in to work with vectors within A-level mechanics. So at GCSE, you are likely told that vectors described displacement in space, and it was how you got from point A to point B, the instructions to move from A to B. You were told that vectors had two properties, their magnitude and their direction. Magnitude being the length, the size of the vector, and direction, the instructions of how to get from A to B. Now some notation. Typically at GCSE, we use the endpoints to define a vector. So the vector AB, and we'll draw an arrow letting you know the direction between A and B. CD, FP, etc. Sometimes the actual vector itself, the line segment of the vector, was labelled with a letter. And finally, especially with transformations, you were introduced to column vectors. So the instructions written in a column vector. The horizontal instructions at the top and the vertical at the bottom. So 4 to the right and up by 2. So 3 different ways to represent a vector, and we will continue to make use of these through the A-level course, and we'll introduce one more. Okay, so let's talk about vector equivalence. We would say two vectors are the same if they have the same magnitude and they have the same direction. So they don't need to be drawn in the same place on a diagram. They don't need to have the same endpoints. But if they have the same magnitude and they have the same direction, we would say these vectors are equal or equivalent. Now, another key feature is that these are also going to be parallel, which, when we look at things from a geometry perspective, that can be quite important. Okay, some non-examples. These are not equivalent vectors. Yes, they may be the same length, they're not going in the same direction. Yes, they're going in the same direction, but they're not the same magnitude. Now, vectors can be multiplied by scalars. If you're multiplying by a positive scalar, we're not changing the direction, we're only changing the magnitude. So, here's the instruction, or the vector 2 to the right and up by 5. 3 repetitions of that, 3 sets of that. Overall, we have 6 to the right, up by 15. I did mention positive scalars. You can multiply it by a negative scalar, and that would instantly change the direction. The vector now represents movement in the opposite direction. Parallel vectors. If one vector is a scaled version of another, we have two parallel vectors. I can say that A equals lambda B, A equals 5B, A equals 2B, A equals a half B. If there's this linear relationship, then one is parallel with the other. That includes negative values. If A equals negative B, A and B are parallel. And finally, vector addition. We know that if we follow two vector instructions, they can be simplified into one. So if I follow the instructions for A plus the instructions for B, the overall vector, the resultant vector, is going to be vector C. If my start point is A and my end point is B, I could write some new instructions which would be C. We could rearrange and say that B equals C minus A. So there is some manipulation we can do around vector addition. Now let's have a look at how vectors are used with the variables that we work with in mechanics. Some of these variables are vectors and some of them are scalars. If we're referring to anything as a vector quantity, it's going to have magnitude and direction. A scalar quantity only has magnitude. So here are some equivalencies. Displacement is a vector quantity. We're interested not just in the magnitude, but in the direction. When it comes to distance, we're not so interested in the direction. We just want to know its magnitude. Velocity. This is the one that most students know already. The velocity of a particle or an object is its speed, but also its direction. So, a velocity of 5 or negative 5. That lets you know what direction the object is moving in. If you're just asked for its speed, we're not interested in the direction, we just want to know the magnitude of its speed. Acceleration. Now this one can both be a vector and a scalar quantity. So sometimes represented as a vector and sometimes just a scalar where we just want to know its magnitude. Forces, once again, can be vectors and can be scalars. So just so you know, when you're asked for displacement or velocity, it must be a vector you're responding with. When you're asked for distance or speed, there's a built-in clue, we're looking for the scalar quantity. Acceleration and forces, it could be either. Let's start with some one-dimensional vector variables in mechanics. So, it's always going to be important to decide on a positive direction, and then we'll measure everything in comparison to the positive direction. In this example, we've been told that a particle starts at a velocity of 10 meters per second at point A. It decelerates uniformly to point C, where it instantaneously stops and returns to point A. So, here's a diagram of the journey that this particle is on. It starts with a velocity of 10. We're going to make the initial direction of movement the positive direction. So A to C is going to be the positive direction. At the beginning of the journey, displacement, we use S to talk about displacement, is 0. Its velocity is a positive speed. Its velocity is 10, since it's moving in the same direction as our positive direction. Its acceleration, however, is negative because it's slowing down. We were told in the question that it's decelerating. As we think about its journey, we just need to think, is the velocity increasing, becoming a larger number, or decreasing, becoming a smaller number? As this particle makes its way to point B, we'll check these variables again. Its displacement is now positive. Compared to where it started, it is in the positive direction. Its velocity is positive. It is moving in a direction that matches our positive direction. Its acceleration, however, is still negative. It is still reducing its velocity. Eventually, its velocity is going to get to 0. And we know that that happens at point C. At point C, its displacement is still positive. Its velocity has now become 0 because we were told it instantaneously stops at point C. Its acceleration is still negative because its velocity has been reducing all this time, from 10 to 7 to 4 to 3 to 0. And actually, its velocity is going to continue to decrease. Now this particle is going to start to move back towards A. Its displacement is still going to be positive. It's on the right-hand side of where it started. Its velocity, however, is no longer matching the positive direction we chose. We chose moving to the right to be positive. So its velocity is now negative. It's moving against the positive direction initially stated. Its acceleration, as it's been for the whole of this problem, is still negative. And finally, the particle returns to part A. Its displacement is back to being 0. Its velocity is negative, and its acceleration is also negative. So to work with these vector variables correctly, we needed to have chosen a positive direction and be referring back to that positive direction. So to make it clear to you, in mechanics, you are going to need to visualize the situation that's happening, what movement is happening. The question won't always be able to define this for you. This is why this is applied maths. It's you thinking through the context and trying to apply some of your own imagination and visualization to the scenario presented to you. Let's have a look at 2D vectors. Now we'll start with the unit vectors. A unit vector is any vector that has a magnitude of 1, and the two default important unit vectors are I and j. I is a vector which is moving 1 unit to the right. J is a vector which is moving 1 unit up, and we refer to these as the unit vectors. Here they've been written in column method. So we should be able to describe any transformation, any journey in terms of how many steps to the right and how many steps up. So how many I vectors and how many j vectors. We can use fractions, we can use negatives, we can write any vector. So this vector is 4 to the right and up by 2. We can refer to this as 4i plus 2j. So we could go through those steps of multiplying a scalar by a vector. So we have 4 steps of I, 2 steps of j. Altogether, this gives us 4, 2. So these are the 2 most common forms of vector notation you're going to use. 4i plus 2j is the same as 4, 2 as a column vector. And there is some expectation that you'll be able to convert in between these quite rapidly. I have a preference for column vectors, and I think you'll see soon that they're so much easier to work with when there's any sort of calculation or resultant vector to work out. So here we have 2 examples. You can pause here and try a few. Can you convert these from ij notation to column vectors and from column vectors into ij notation? Be on the lookout for when there is no I component or no j component. Be on the lookout for when there's a 0 within the column vector. What does that actually mean? Okay, pause here if you want to try these out. And here come the answers. Okay, can we manipulate these vectors? Can we combine them together? Let's look at making a resultant vector. Here we've been told that the vector A is 3i minus 2j and the vector B is negative 2i plus 3j. We've been asked to find A plus 2b. So here they are written as column vectors. And starting with A, I want to add on 2 sets of B. So the vector for A plus 2 multiplied the vector for B. Multiply the 2 in. We'll just add together the horizontal components, and we can add together the vertical components. 3 minus 4, negative 2 plus 6. Our overall resultant vector, negative 1, 4. You can convert this back into ij notation. It's not necessary unless the question's asked you to. Usually, both the column vector and the ij notation are acceptable for a final answer. Now, most times when we're drawing a vector, I hope you can see that there's a triangle superimposed in the background. So we should be able to do some maths with those triangles. The first thing we want to look at is finding the magnitude of a vector. So this is going to be the length of the vector A. The triangle that exists in the background has a base of 4, a height of 2, and is a right-angled triangle. Immediately, when we say we're looking for the length A, we should be thinking of Pythagoras. We can use some Pythagoras to find the unknown length A, to find the magnitude of this vector. We write these bars, these modulus bars, to show we're finding the magnitude of the vector A. From that, we can just process the Pythagoras, and we get root 20, which simplifies to 2 root 5. The magnitude of this vector is 2 root 5. In addition, we're often asked for the angle that a vector makes. Once again, we have a right-angled triangle. Now we're looking for an angle, and I hope that makes you think of trigonometry. Once again, let's label the lengths that we have for these components, and these components should always be drawn with dashed lines. Never with a solid line, always with a dashed line. So, if we're trying to find this angle theta, we know we're working with the opposite and the adjacent, so that's tan. Tan theta is 3 over 4. Inverse tan, on your calculators, we get theta equals 36.9. Now, there are many vectors that have an angle of 36.9. To be more specific, we either give our answer as a bearing, so the bearing would start measuring from north and go clockwise, so it would be 90 plus 36.9, which would be 106.9. Or we just add a bit more description to what we have. This is 36.9 degrees below the x-axis, below the horizontal. So we can refer to the horizontal, we can refer to the x-axis, or we can write it as a bearing. Trigonometry helps us to find an angle, which we use to describe the direction that the vector is going in. Okay, so let's use that in mechanics now. We know that a vector quantity, such as velocity, has an equivalent scalar quantity. So, if I had a velocity that was 5i plus 9j, to turn it into a scalar, to find its magnitude, I would need to use Pythagoras. So the square root of 25 plus 81, that's the square root of 106. That gets us a speed of 10.3 meters per second. So the velocity was 5i plus 9j meters per second, whereas the speed was 10.3 meters per second. You can easily convert a vector into a scalar, but the scalar won't go back into a vector because there are many vectors that have this scalar answer, and we wouldn't know without additional information which vector to return to. So another vector scalar pair are displacement and distance. If the displacement was 2i minus 4j, we could then say that the distance, using Pythagoras, is going to be the square root of 2 squared plus 4 squared, so the square root of 20. And that gives us an answer of 4.47 meters. So the displacement as a vector and the distance as a scalar. Velocity as a vector, speed as a scalar.